Alright, hey guys, what's going on? So today we are going to be covering quantum field theory. I know I have a playlist on this channel already. This is the playlist on quantum field theory that I have on this channel already is sort of how I kickstarted the channel. And retrospectively, I looked back on some of those videos, looked at some of your guys' comments, and realized, I could have done this better. There's some information out there that I felt like could have been done a little bit better as well. So we're going to go ahead and we're going to recommunicate, if you will, quantum field theory. And so this is going to be more visual. There's going to be a lot more images. This is, as I continue with this channel, the images and the figures are going to be a lot nicer. So again, this is quantum field theory. As I've mentioned before, if you contribute to the channel, you'll be able to get an overall canonical view of quantum field theory. You'll have access to all of the other videos as well. This is going to be in the silver tier, around $7. Keep in mind that when you make your contribution or when you subscribe, not only do you get access to this video and future videos to come in this particular playlist, but other videos as well. You get access to those and those playlists. So without further ado, let's go ahead and get started. We are going to talk about quantum field theory today, and we're starting fresh. We're going to start with the Klein-Gordon equation. We're going to spend a couple of videos on that, and then we're going to dive into the Dirac equation and so forth. So, like I said, I started off this channel with QFT about a little bit over a year ago, probably, and so I'm going to revisit this topic, and I'm going to talk about it a little bit more efficiently, a little bit more better, and with more visuals. What are my sources here? Well, in my last video, or my last playlist, I primarily focused on nonsense quantum field theory. We followed that chapter by chapter and all the way through. Okay. Now what I'm going to do is I sort of had intentions of following just this one, but over the past few months, I would say, I debated incorporating other books into here, and so I decided, instead of just following this one, we're going to follow this along with these other ones, okay? And we're going to try, we might bounce between the two depending on depending on the content, if you will, right? And so these are my sources. Introduction to Quantum Field Theory by Peskin and Schroeder. This is probably the most famous of the books, and this one as well is probably one of the more famous ones as well. This is Quantum Field Theory and the Standard Model. This one I don't really see talked a lot. It's a really good book, though. I like it a lot. It goes in depth derivations. This is quite nice. This one, again, as I've mentioned, this one's quite nice as well if you're just getting started into QFT. Quantum field theory in a nutshell. This one's talked about quite a bit too by Dr. Z. It's a little bit less popular, I think, but I like it. It goes through some nice derivations. It makes some concepts clear. And then this one as well, I don't really see talked about as much, but I came across this one not too long ago and decided to go through it, and I thought it was some of the explanations I thought were kind of illuminating. So we're going to touch through all of these. Let's go ahead and get started. So we're going to go in quantum field theory in a way that made more sense to me when I was going through it, but this time with illustrations, and hopefully this is going to be useful to you as the reader of these books or as the consumer of this content. We're going to start with classical field theory, as most quantum field theory does, okay? And along the way, we'll touch upon special relativity instead of dedicating like 1, 2, or 3 videos on just recap of special relativity. We're going to sort of, as we go, revisit those topics in special relativity, because I don't really want to do like recaps or reviews on special relativity. I want to kind of just jump into this. So what are fields? Well, a field is just a function of space and time. That's really fundamentally what a field is. Okay, it's some value that depends on where you are in space and when you are right? So some examples include scalar fields, such as the density. The density can fluctuate with time. The flow of a river, for example, is another. That's not a scalar field. The flow of a river would be a vector field, right? Temperature can also fluctuate in time, and it fluctuates in space. So this. So we have scalar fields and vector fields. There's other different types of fields, right? There's tensor fields, right? That's general relativity. So you have a metric everywhere in space and time. You can also have, so you have tensor fields, you have scalar fields, you have vector fields, you can have twistor fields, right? So a twistor is something we haven't gone into quite a bit, but I want to, and I'm starting to make videos on that. But we can have twistors. Fundamentally, the difference between all of these things, and we'll get into this a little bit more, is that scalars transform in some unique way under some coordinate transformation, whereas vectors transform in a different way. Tensors transform in a very unique way as well. But all of these things, they're defined by how they transform under coordinate transformations, okay? So I just have some examples here. We're probably most familiar with scalar fields and vector fields, and I have different configurations of each, right? So this is one configuration of a scalar field, this is another one, and another one, right? So red being very high values in number in a scalar, or blue being very low values in our scalar value, or in our scalars, right? Vectors, they can have high magnitude, like long vectors here. They can have low magnitude, which, like the short vectors over here, they can all be uniform. But again, they're all existing. They have a vector everywhere in space and time in some volume, okay? And we have, my apologies for the dog barking. Let's see if my pen is a good thickness. We have our volume as well, right? So this is the temporal dimension, this is the x dimension, this is the y dimension, and then we have a suppressed z dimension as well. I can't draw four dimensions, but you get the point there. All right. So from these fields, we construct something called an action. Now, this action is also called a functional because it's a function of functions, and so we call a function of function functionals. And we write an action S in this way. And an action is an integral of some function, or what we're going to call the Lagrangian. L is the Lagrangian, and it's integrated over time. This can also be written as a Lagrangian density over some volume, some 4 volume, okay? And so the 4 volume, again, it's a volume in space-time. This is what's fundamentally special relativistic about this theory. It's a space-time theory because it's integrated over 4 dimensions of space-time, but time and then the 3 dimensions of space. Phi here is a field and can be more precisely written in this way, where this really means phi of x nu, which really means phi of, well, I have it up here already, right? So I already drew this, right? So this guy there is equal to that, which is a function again of t, x, y, and z, and we can write it in this way as well, with mu running from 0 to 3. Okay, and so that's 4 entries, 1, 2, 3, 4 entries, time, x, y, and z. Okay. The Lagrangian density is a function of the field and its derivative, right? Because we have the field, the position values of the field, and then the derivative of those positions. And we're gonna take a look at this a little bit more as well. So as an example, we can take one configuration of our field, and the output is going to be some number, right? Because here's our field. It has everywhere in this volume, we have some value. Okay, and that value gets put in here, and then the derivative of that value gets put into here as well. So this configuration is going to be put into this thing this function called the Lagrangian. Again, the Lagrangian describes, it's the function that describes the values everywhere in this volume, okay, or everywhere in space, and then we define some particular volume over the bounds of the integral. And then when we do this integration, we're going to get some number. This number is S, okay? And S, I just have some random number here. It says 3.5. Okay, so we attribute some number then to some configuration of our field. So we've effectively placed a label on this particular configuration. Imagine then that we wanted to minimize this action. We would want to find the minimal number for this action. So another way of asking this is, what configuration can we put into here that minimizes this guy? Okay. So, well, from calculus, you might be able to recall that finding the minimum of some function is merely just taking the derivative and setting it equal to 0. Right? So, here, this is what we're doing. We want the small change in s to be 0, and so from here to here, we're just doing a product rule, right? So we're taking the derivative, right? So the derivative of the Lagrangian times the small change in theta, okay? And then we take the derivative of the Lagrangian here with respect the derivative with respect to the derivative here, right? So really what we're doing is we're taking the derivative of this with respect to this and the derivative of this with respect to this, right? So that's, and let me erase this really quick. And then when we do that, we have this guy right here, right? Because we need now to break this thing apart because we need to take the derivative of this. Right, so that's just product rule. And then we use the chain rule. All right, when we use the chain rule, we get this guy, right? Because we want to find the derivative of this thing here, right? So yes, okay. And then when we expand that, right, so we're taking the derivative of this thing times this, and then the derivative of this thing. Right, so that's the product rule, the chain rule. I get mixed up on the names here. It's the chain rule, right? So the derivative of this times the derivative of this here. And so the derivative of these two guys, well, this thing's a small constant, so that's going to go to 0. And so we get this thing. All right. So we said that this has to be 0. And so what we get is this condition here, that this, we can multiply both sides by this. And when you multiply both sides by this, because we have this 0, we have that the rest also has to be equal to 0. So this here must equal to 0. This is our Euler-Lagrange equation. So the Euler-Lagrange equation is therefore the condition that we get when we want to find the field configuration that finds the smallest action. This is arguably the most important equation in all of classical field theory and in quantum field theory. Okay, so effectively what we've done is we've said, well, we want this thing to be minimized, and in minimizing that, we found this equation. And so if we can take some field or some configuration of some field, spit it, or put it into the Euler-Lagrange equations, we should theoretically be able to get something out of that. And that something we're going to claim is what gives us the equations of motion, right? I'm blanking on the name of that, right? So as long as we have the Euler-Lagrange equations, we can find the equations of motion for our system. So let's take an example. So suppose this was our Lagrangian, okay, and we could take this part of the Lagrangian, we take that's this, and so this guy here is going to be, because this is squared, that squared bit is going to come over here, it's going to cancel with the 2, and then we have this guy out here, which multiplies this guy here. This mu can be nu or mu, right? Because they're really just dummy variables or dummy indices. So when we do that, we get this, and then for this part of the Euler-Lagrange equations, this part right here, we get this, right? They have to equal 0, so we get this, bring this to this side, and we get this here, where this bit here is this guy right here. So we have, my apologies for the dog again. When we raise this guy, we can change it to mu with our Minkowski metric. All right, that's going to give us this guy right here. All right, multiplying the Minkowski metric by this thing doesn't do anything, right? Because these are just numbers. So what we get is this guy. Is this guy right here? Okay. So this is d mu d nu, or d mu d mu. This is what we're calling. Again, these are four vectors, right? Because we have d0, d1 plus d2 plus d3. And then our other one, we have D0, D1, D2, D3. And we actually need to change the sign on these guys, right? Because we're working with special relativistic equations. And when we use this Minkowski metric, we're changing signs, right? So we're changing signs there. So we get, when we do this multiplication, we get this guy, and that's this, right? So, and this guy here, so this guy here is d mu. This guy here is d mu. Okay. Let's continue. So the process of minimization is going to parse out all of the other possible field configurations, and it searches for one which we claim is the classically correct one, or the one that sort of dovetails with the classical world. Quantum field theory says something else. It's going to say that all configurations are possible, just not all equally likely. And we'll get into that. That's when we start talking about path integrals and so forth. So we propose the Klein-Gordon Lagrangian over here, right? So this is actually the Klein-Gordon Lagrangian, this thing right here. But now let's take a look at what this actually means. And we're going to dive into what this thing means. And let's go ahead and do that. It's sort of more of from a physical perspective. So let's consider the difference in kinetic energy and potential energy for some spring, right? And we're going to call that our harmonic oscillator, or Lagrangian for our harmonic oscillator. So here's our kinetic energy, here's our potential energy. Now imagine a spring of coupled harmonic oscillators. We will imagine that all of these springs have the same spring constant and are connected by springs with the same spring constant. So we want to know the dynamics of the system, which means that we want to know the positions and velocities of each spring. So let's do a little bit of Pythagorean theorem here. So L is going to be the unstretched spring. L tilde, or whatever you want to call this, is going to be the length of the stretched spring. Q1 is the distance, because again, Q is a position, so it's the distance relative to Q2. So we have this, right? So this is equal to this plus this squared. All these things are squared. So this is equal to this. We can then factor out L squared, and then we can factor out L squared to L because it's in the square root. And then this, we can use the binomial approximation to get this guy. And then from here to here, then, we're saying that the unstretched spring is equal to the stretched springs plus some change, and so that means that this some change is going to be our change in our length. Okay. So the difference between this guy and this guy is this squared, the position of this squared, divided by 2 times this. Right? So this is to say that the difference between the stretched coupling spring and the unstretched coupling spring is proportional to the square of the vertical distance. So the potential energy stored in the coupled springs, therefore, is going to be this guy. Right? So this is the difference between Q1 and Q2. So here's our Q1, here's our Q2. Okay? The potential energy, again, is we're going to say 1 and 2, not 12, right? This is potential energy V between 1 and 2. Okay, then we have our spring constant, or this constant that we have out here, 1 over 2L, and then 1/2 K, that comes from our Hooke's law, for our potential. Okay. All right. So this is basically Hooke's law. So the difference between our kinetic and potential energy then is now, so our kinetic energy is this guy, our potential energy is now this guy and this guy. Right? So this guy is the potential energy within each spring themselves. This is the potential energy that's stored between the coupled springs, the springs that are coupling them together. All right. And so we can go here now and we can say, well, again, this is just position. These are just positions. We have an L out here. So this thing right here is just here. Okay. So this squared. Okay. So this looks like a derivative, a spatial derivative, right? Not a temporal one. This is a temporal derivative. This here is a spatial derivative. This spatial derivative is, together, this looks like we might be able to use some special relativity, combine the spatial and the temporal derivatives, and so we'll see how that works. So we now rename the coordinates of each spring. Okay, so this is important. This is how we're gonna get into field theory, right? This idea here is QIT. Well, QI now becomes phi of x, right? So this QI here becomes this phi of x in the continuum limit, right? So now we're saying every point in space and time in the continuum limit. Okay, so this is, we'll write the continuum limit. This becomes a continuous field. Okay, this is really becoming a continuous field, and so QI, these masses, right? These masses Q1, Q2, Q3 become points in space, right? So QX. So we can think of our space then as looking something like this, where each spring, this gets a little bit blurry as I zoom in, but each spring has position, right, given by phi of x, and then it's going to evolve in time as well. So we can think of each one of these springs, they all have the same spring constant, okay, but we can think now, oh, actually, that's symbols, I spelled that wrong. We can think of this redefinition as giving dynamics to space, which all points are in which all points are connected by a spring with the same spring constant. So in the continuum limit, our summation symbols become integrals. Okay. So all these become integrals, as we can see here. This becomes an integral. This thing has this becomes an integral. So we're integrating now over space. We have to integrate also over space and time, right? Because this thing is temporal, okay? So this is shorthand. I'm going to be doing a lot of shorthand because that's we'll hopefully get used to the shorthand because that's what a lot of quantum field theory does, is a lot of shorthand. But the idea here now is that we want, I've also labeled equations. This here is the kinetic energy of each mass. So we come up to this picture. Each one of these little dots has kinetic energy to them. Each one has some potential energy. And then the coupling between them has some potential energy as well. All right. So we can rewrite the temporal and spatial derivatives then in this way, in a way that special relativity demands. We need a C in there for that. And so what we get then, we can couple these two things together. This should be squared, right? This thing should be squared. This should be squared like that. And so we can combine then this guy and this guy into our upper and lower derivative symbols here, right? So again, d mu is equal to dt or dt minus d dx minus d dy minus d dz, and then d upper mu, well, that's just the signs are changed when we use special relativity, right? So plus d dx okay, dy plus d dz. We can compare this with equation 2 and see that the form is exactly the same. So therefore we could say that the Lagrangian represents the difference between the kinetic energy and the potential energy of a coupled spring system. So we go back here really quick, and we have, let's erase some of this. This is really this, we've really recovered this thing, which is this, okay? This is the spatial derivatives, this is the temporal derivative, and here's our mass. Same thing here. We have our spatial derivatives and temporal derivatives in this, and then we have our k, which is going to act as like some mass term. All right. So that is going to be the first video. We've really just talked about, okay, so we've talked about the Euler-Lagrange equations. We've talked about a little bit on the Klein-Gordon equation, right? Because this here is the Klein-Gordon equation. This here is the Klein-Gordon Lagrangian. And so what we've been able to do is we've been able to say, well, this guy, the Klein-Gordon Lagrangian, gives sort of birth to the Klein-Gordon equations. What we need to do now is we need to take a look at the solutions. What exactly are the solutions? What does phi have to look like in order to satisfy this equation? And so in that, we're going to cover that in the next video. So with that being said, make sure to hit that like and subscribe button, and I'll see you guys in the next video.